Ma'am, you can start.
Good morning, one and all. I, Rani, Assistant Professor, Department of Electronics and Communication Engineering, wholeheartedly welcome you all to the session 4 of FDP on Machine Learning Applications on Image Processing. I would take this as a pleasure to welcome our speaker of the section, Dr. Satish Kumar Singh, Associate Professor, IIT Allahabad. Welcome you, sir. Dr. Satish Kumar Singh is with the Indian Institute of Information Technology, Allahabad, India, as an associate professor at the Department of Information Technology from 2013. Before joining IIT, he served the Department of Electronics and Communication Engineering, JIP, University of Engineering and Technology, Guna, India from 2005 to 2012. He has about 16 plus years of professional experience in various capacities. His area of interest include image processing, computer vision, deep learning, and pattern recognition. Presently, he is heading the computer vision of biometric lab at IIT Allahabad from 2015 onwards. He has supervised 66 PhDs and 34 master students in his research career, and presently 9 PhD and 6 master students are doing a research in computer vision and biometric lab. Now we can go to with the section, sir.
Thank you very much for the introduction, and
Welcome you, sir.
so I'm thankful to the organizers, Dr. Rohit, and other organizers for inviting me. Uh, I request all of you to mute your mics so that we can avoid the disturbance. I request all the participants to mute their mics. Thank you. So, not taking much time, let us start the discussion. Hello.
Yes, sir.
Okay. So, all of you are requested to mute your mics, please. And whenever it is required, then we can have the discussion. Thank you.
Right, sir.
So, let us start the discussion. I'm just sharing. My screen is visible.
Yes, sir. It is.
Can you see the presentation?
Yes, sir. Yes, sir.
Okay, thank you. So, as a theme of the faculty development program is the machine learning and applications in image processing. So I'm going to talk a little bit more specific, and I have chosen the topic of the day, of this particular lecture or discussion is deep learning architectures for image processing applications. So basically, I just want to give some abstractive view of deep learning architectures and how these deep learning architectures are going to be used for a variety of not only image processing applications directly, but other applications where image processing will be used as a necessary step. So directly or indirectly, applications are related to some sort of image processing for some suitable applications. So the content, I'm not claiming that all the contents are from our side only. So content used in these slides are adopted from many sources for academic purposes. Broadly, the sources have been given due credit appropriately. However, there is a chance of missing out some original primary sources. The authors of this material do not claim any copyright of such material. So, before starting, let us discuss about some very essential points. Okay, if we are going to discuss the deep learning, machine learning, and many other things, then we should be very well aware of these basic but essential points. Like, Artificial intelligence, before moving to that, what is the meaning of artificial intelligence? Then many people may say, pardon. So many people may give certain answers regarding this, what is artificial intelligence. Okay. But as per my opinion, and not only my opinion, but in general, artificial intelligence is equals to learning plus generalization. So with this very simple mathematical equation, we can understand. So AI is equals to learning plus generalization. Okay. So basically, the machines should be able to perform certain tasks. So machines, if we talk about the machines, so there may be some electromechanical machines. Okay. There may be some computers. There may be some decision systems, or whatever it is. There may be smart camera. Okay. There may be autonomous vehicle. There may be some robots. There may be some automatic game players or digital game players. Okay, so many things are possible. So AI is learning plus generalization. So before understanding about the actual meaning of AI, what is learning and what is generalization should be known to all. So AI, learning plus general. Then what is learning basically? Okay, so learning can be defined in a way. Suppose we are being presented with variety of examples. Okay, large number of examples. Okay, so what happens with the help of these examples? We are learning something. Okay. Say we need to cross the road. Okay, so there is a process, and this process will be learned by our brain. And every time we will follow the same process to cross the road. Means watching left, right, no vehicle, then we can cross. I mean, this is general thing. So these kind of examples will be presented to the machine, and machines will learn. So in crude words, we can say this is a kind of memorization and association. Means simply on the basis of examples, their outcomes will be associated. And whenever this kind of example will be presented to the machines in future, same kind of outcome will be thrown by the machine. So this is simple process of learning. Means learning with the help of past examples. Okay, so humans used to learn this way. And how machines? So machines will learn on the basis of past data. So more variety of data, more learning is possible, isn't it? So learning by experiences is analogous to learning by data in case of the machines. Okay. So what is, if it is learning, then what is the generalization? Okay. So generalization can be defined in this way. Suppose we have learned from some past examples. We have learned from some past examples. Okay. But somehow in future, we are getting a situation which was never presented to the human, or you can say the machine, to the machine. Okay. So this present scenario is entirely new scenario. Okay. Then how humans used to take the decisions? Based on some past experience, they used to generalize it. Okay. Although the situation was never presented before, even then humans are able to take certain decisions, certain useful or certain appropriate decisions. So this is the generalization capability of the humans. But how the machines will attain this generalization capability is the question. So normally, just to include more and more generalization power to the machine, what happens? Whatever data will be presented. Okay. So slightly varying data for the same set of outcome will be presented to the machine. So that machine will learn not only with the actual data, but with some form of the noisy data. Some form of noisy data means slightly deviating data or slightly noisy data. So if machines used to learn with this kind of thing, then this is simply the generalization capability. Means if you want to improve the generalization capability of any human or machine, then human or machine should be allowed to learn with the slightly deviated or noisy data. Okay, so only learning is not sufficient to qualify a machine as artificially intelligent enough. It means it should have sufficient learning capability, it should have sufficient generalization capability. Learning capability, okay, so if you want a better learned system, then what is required? What are the basic requirements? First of all, you should have sufficient set of examples, sufficient data. Okay. At the same time, you should have sufficient memory, because I have already told that learning is associated, or learning can be considered as the memorization with association. It means memory is required. So if you want that a person should be more learned, so what are basic requirements? More and more examples must be presented to this person or machine. Getting? So if more and more examples are presented, then what is required? More time is required. So consider a scenario. Suppose there are two persons. One is only 3-year kid and one is 30-year man. So whom you consider that will be more learned? 30-year person who has faced large number of examples or large number of scenarios will be treated as more learned. That is immaterial whether this 3-year or 30-year persons have attended any formal training or formal schooling or not. Got it? So for learning, more data or more experiences are required. At the same time, more memory is required. More memory is required. If memory is not sufficient, then what will happen? If large number of experiences are presented, then it cannot be contained into that part of the memory. So that's why brain used to develop. As experiences are faced, and slowly the brain also used to develop, so that the essence of those experiences should be kept or should be contained into that part of the memory. So this is the thing. Data driven, modern systems are basically data driven. Huge data is available with us. So that's why huge memory space is required for better learning. At the same time, better generalization is required. If we want to generalize the system more and more, then more noisy data is required. Again, data is increased. So more memory will be an essential part of modern artificial intelligence systems. So how kid used to learn? Suppose there is example of kid learning the apple. Okay, because I just want to highlight few points from this particular example. So how kid learn apple? So this is very simple. A kid who has never seen the apple. Suppose you want to enable the kid to learn the apple, then an apple will be presented to the kid. Okay, and kid will see apple and you will say, okay, this is apple once. But next time, if you present the guava, then what outcome will be thrown by the kid? Kid may say, okay, this is apple, isn't it? Because kid have learned, kid was presented with only one example or only one instance. Then what happens? Again, you present apple and say, this is apple, this is apple, this is apple. Okay, means you present one kind of apple. It may be red, having certain shape, certain weight, certain size. Next time you may present some different apple having different shape, size, color, texture, etc. So every time you used to present large number of apples to the kid and kid observe it and then learn that this is apple. Okay, so eventually the kid will be enabled to learn the apple. But what happens? Every time you have, for entire life, you have presented only apple to the kid, isn't it? Then what will be the outcome? Whatever fruit will be presented to the kid will say always, this is apple, this is apple, this is apple. So why I'm saying there is underlearned system, means less examples have been presented despite having a better memory space, or overlearned system, means this is completely biased kind of system, means whatever will be presented, but every time the kid will say that this is apple. Okay, so basically there are certain problems. These problems are simply known as the underlearning or overlearning, or somehow related to the bias and variance. Somehow related to the bias and variance. Then how to optimize this bias and variance to produce or to generate the better system? Means entire machine learning, means the task of entire machine learning or deep learning systems are to optimize the bias and variance. Okay, so the system should neither learn less nor learn more. Learn more means it may be biased towards certain outcomes. Underlearned means insufficient data has been presented, means insufficient learning or overlearning. Okay, so artificial intelligence means good learning and good generalization capabilities. So artificial intelligence means, the earlier definition of the artificial intelligence was, means machine should be able to do certain tasks, certain actions. So if we talk about ancient artificial intelligence systems, then these artificial intelligence systems were basically the rule-based systems. Okay, it means we used to do some sort of programming, and depending upon those protocols, certain rules, the decisions were made. So these were earlier artificial intelligence systems. Okay, this is general perception, means rule-based systems. Then what is the difference between artificial intelligence and machine learning? So machine learning is a part of, subgroup, or you can say subdomain of artificial intelligence. So, but where is the difference? In case of artificial intelligence, everything was, you can say, the rule based. But in case of machine learning, the data was presented with the help of some features, means some useful features were extracted, and machines were basically taking the decision. Means the classifier or the decision maker was basically the learning based systems. Means these features were treated as the examples, and machines were learning on the basis of those features. Okay, so machine learning based systems were basically, means feature engineering along with some learning based classifier. Okay, so this was the machine learning. But if we talk about the deep learning, so there is a transition. Artificial intelligence, some sort of programming or rule based system. Machine learning, some feature extraction and learning on the basis of those features. But in case of deep learning, so huge data is available. So what happens? This is kind of end-to-end process. Means there is no need to make any rule, first of all. There is no need to draw any feature. Okay. And entire process means whatever rule, whatever features will be extracted will be automated in nature. Means automatically the feature extraction along with the decision making will be done. And this is the beauty of the deep learning. Because now you're having huge data. So large number of examples are available to enable any system to learn and to generalize. So that's why it is possible. So in case of deep learning, nothing is, no rule-based systems, no feature extraction, nothing, and this is totally end-to-end process. So what next? I just want to highlight few more things. In case of the deep learning, what in present era, what is happening in almost every domain, we are having huge data. Okay, and inferences can be drawn out of this huge data by using good compute machines. Obviously, machines will be required to compute. Otherwise, you cannot do the deep learning processes. Okay, so this is the state of the art. But where we are moving now? Now people started talking. Suppose we have deployed a face recognition system, then this face recognition system may be biased toward men or women, maybe old aged or new age people. Okay, and they're biasing. There may be any kind of biasing. There may be biasing towards a particular skin tone, or maybe some sort of skin appearance, or the feature or the facial appearances. Okay, so what happens? But in case of the humans, what happens? These kind of biases are not available, isn't it? So in some cases, bias-free machines will be required, like in case of facial recognition. But in some cases, some decision makers or some decision-making machines, human aspect is very important. What is human aspect? Human aspect is simply the cognitive aspect. Okay, cognitive aspect. And what are those cognitive aspects? How to understand? Suppose there is a decision maker. There is maybe some head of department or director or whatever it is. Okay, so what happens? For every set of problem, there may be a problem. Means there may be two instances where the problem is same for both the instances, but the decision as made by the administrator may be entirely different. So how those decisions are coming different if the problem are similar or the same? Because of some intrinsic and extrinsic reasons. Those intrinsic and extrinsic reasons will be inspired by cognition and emotions and other high-level processes of the human brain, basically. Getting the point? Means the decisions by the administrators are inspired by those intrinsic and extrinsic reasons. That's why decisions are totally different. And sometimes machines, it will be required that machines should also take the decision in the same way. Means there are two contradictory situations. One is completely bias-free. Second is human-like decisions. So human-like decisions cannot be bias-free all the time. Okay, so people are moving in this direction. Okay, so depending upon the situation, machine should behave completely bias-free, or it should behave just similar to the humans, which are inspired by cognition and emotions and other things. So cognitive inspired, emotionally intelligent deep learning is the future. So machine learning versus deep learning. So most machine learning methods work well because of human designed representations, means some sort of features and input features. Human design, representation and input features. Okay, means how those features will be used and what set of features should be used by the machines. Okay, suppose you need to describe a fish, then what is the length of fish, what is the appearance of fish, okay, what is the weight of fish, or maybe another another set of representations, means other set of representations. Okay, so this way you need to define. Means machine should understand on the basis of certain measurable inputs. Okay, so measurable inputs are simply known as the features. So machine learning becomes just optimizing the weights. Okay, so this is evident that optimization is necessary. Only weight, this bias and variance optimization will be required. So you can treat the machine learning system as only optimization system. So machine learning in practice, describing your data with features a computer can understand. So if it is measurable, some quantity, okay, some logical or some arithmetic values, then it is, I mean, your systems can understand. And at the same time, learning algorithm will be used, okay, where the input will be the described features. So learning algorithm will optimize the weights on input features. So this was typical machine learning models. So then what is the deep learning? A machine learning subfield of learning representations of data. How to represent the data, and it will be done automatically. Okay. Exceptional effective at learning patterns. It means deep learning automatically used to represent the data. And on the basis of this representation, learning will happen. Deep learning algorithms attempt to learn multiple level of representation by using a hierarchy, multiple layers. Okay. So now there is a question. When a model or when a learning system will be treated as a deep learning? So there is obvious answer that many people will say, okay, the 5-layer, 6-layer, 7-layer neural network will be treated as a deep neural network. Okay. These are some very vague answers. I mean, there is no absolute answer that which models will be treated as deep models or deep architectures or deep learning systems. Okay. So please remember that hierarchy of representation is essential term. To be a model, to be a model, to behave as deep learning model means for any deep learning model, hierarchical representation is necessary because deep learning is somehow related to the human brains. Human brains are very deep. Okay, so human brains used to behave in hierarchical manner. That's why any model will be treated as deep model if it is using the hierarchy of the features. So hierarchy of features at multiple layers, obviously at multiple layers, I mean multiple layers will be required to present the feature hierarchy. Otherwise the model will not be treated as the deep model. So hierarchical representation is necessary. So if you want to provide the system tons of information, it begins to understand it and respond in useful way. Okay, it means tons of information, more and more examples, more and more examples. So what do you think that more and more memory space is required? So if more and more memory space is required, then how this memory space will be created and which things will be treated as the memory space? So basically, suppose, just a minute.
Excuse me, sir. Can I ask?
Yes, yes.
Sir, can you take a simple example for differentiating this machine learning and deep learning? A real-time example.
Real-time example of?
Which differentiate machine learning and deep learning.
Yes. In case of machine learning, what happens? Suppose you have I'm just taking one example, that is a fish. This is very popular example if you have gone through this through the heart. Okay. So this basically there must be some appearance. Suppose this is the appearance of a fish. Okay. So if you present this model to system, then how this computer should understand that this is a fish or not. Suppose this is a simple problem, whether this is a fish or not, how the computer should understand. Okay. So how computer will understand? So what ways will be there? What is the length of the fish? What is the weight of the fish? What is the color of the fish? And there may be many more features. Okay. So this is fish class C1. There may be another fish class C2. Okay. For class C1, there may be variety of examples. Means variety of fish may be there because length may be varying, weight may be varying, or color may be varying slight variations. So you need to represent, suppose this is x1, x2, x3, suppose. and there is another class of fish, then this may be y1, y2, y3. And there is a slight chance that these may be slightly varying. Okay. So now there is a model. Okay. This model will take these as input and will take the decision. Okay. And what maybe the decision, what model will be used? Suppose we are using the SVM, or we are using decision tree, or we are using even neural network. Okay, these kind of classifiers can be used. Means depending upon this distribution, x1, x2, x3, that is three-dimensional data here, because the feature vector is only three-dimensional. Then these models will be trained. Variety of machine learning models are there. Okay, so this way it will learn. But in case of deep learning model, this image itself will be presented. And rather than forming this x1, x2, x3, what will be there? Suppose you have presented an image, then at this level, there may be some feature, maybe line, there may be some edges, etc. At other level, there may be some more abstract features. And this abstraction will keep on increasing. But these features will be, generated. Okay, at the top layer, the most abstract feature will be generated. Okay, and since this is labeled, what will happen? Depending upon this feature, decision will be made, and then again, if it is, error will be calculated and it will be back propagated, and whatever weights will be there in between will be optimized again. So one by one data will be presented. Some lower to middle to higher to highest level features will be generated automatically, and depending upon those features, the model will learn itself. So there is no need to find out the length, weight, or color of fish. Getting the point? So for C1, the data will be presented. Suppose there were 100 examples, 100 data points for C1 and 100 data points for C2, both will be presented, and then these weights, means in between whatever weights will be there, like these, will be trained or will be optimized. So this is the difference between the machine learning and deep learning models. Hopefully you might have got information.
Yes, sir. Thank you, sir. Thank you.
Okay. So this is some elementary thing. Okay. So what is learning? We have already discussed, means some sort of memory is required. And one more thing, I have already told every model will not be treated as a deep learning model. So feature hierarchy is essential. As here we have seen that this is the low level feature, this is the low level feature, this is the mid level feature, this is the high level feature. It means feature hierarchy is generated. So this kind of model will be treated as a deep learning model. But the same thing can be done by this kind of example. Suppose there is a neural network. So these are the inputs, suppose x1, x2, x3, or you can say x4. So what is this? This is 2 by 2 image. x1, x2, x3, x4. So 4 pixels are aligned this way. And there are some hidden layers. And how many hidden layers? Infinite numbers. Okay. So what will happen? These will be connected this way. All 4 will be connected here. All 4 will be connected here. Getting the point? Similarly, this way the connections will be made. Suppose this kind of decision need to be taken. Okay. Similarly, here also. This is C1, this is C2. Suppose these are the output nodes for class 1, class 2. Input feature size was 4. Suppose all pixels in raw format has been given, and pixel itself has been treated as the features. Okay. It means infinite number of hidden layers has been taken. Okay. So it means if you go through the Covert's theorem, it states that only 3 layer net is sufficient to draw any complex decision. It means any hypothetical most complex decision boundary. Okay, means it is, suppose there are two classes. Suppose class 1 distribution is like this. So this is class 1. Within that, this is class 2. Within that, again class 1. Suppose very jumbled classes are there. Means distribution is in such a way that it is completely jumbled. Even then, you can draw all those decision boundaries with the help of only 3-layer net, depending upon, on the basis of the covers. But what is there? Will this network will be treated as a deep network? No, it will not be treated as a deep network because feature hierarchy cannot be generated. But the problem can be solved with the help of this kind of network as well. Where is the problem? Then if this network was able to solve the problem, then where was the issue? Why we have moved to the deep network? Obviously, here large number of weights are there. Huge memory space is available. Memory space is very huge because large number of connections are there. Okay, but where is the problem? Problem is simple, because since there are an infinite number of nodes, so how many weights? Weights are also infinite. If weights are infinite, then it is very difficult to optimize these kind of networks. That's why the neural network research was completely died around 1980. 1980 ke aspas, it was completely washed out and people stopped doing research after 1980. There were only few groups who continued to do the research. Okay, because problems were solvable, means non-linearly separable classes were separable with the help of these kind of networks, but ultimately at the cost of huge infinite number of weights, and this could so that's why people move to the deeper or deep networks. Okay, so improving performance through experience is simply the learning and getting computer to do well on a task without manually building in computer.
Sir, I have a question. Can I ask, sir?
Yes, please.
Sir, generally in most of the objective questions, they ask how many neurons are required. So how many layers are required. So how do we understand that, sir? Can you?
Yes, very simple. Very obvious question. Normally, we treat the deep learning as a black box, isn't it? Means we hit and try. Okay, these many layers. Some researcher is reporting the result on 5 layers. Some researcher on 7 layer, 10 layer, etc. But what should be the intuition behind choosing the number of layers? So I give very simple example. Here, one of my PhD student did research on signature verification. Okay, suppose the signature is like this. Okay, we have signed like this, isn't it? Sometimes this pen is red, sometimes the pen may be blue, sometimes green, and this background is sometimes completely white, sometimes faded white, sometimes shaded, isn't it? But we have applied very deep neural network and we tried to analyze. We simply increase the number of layers. Then what happens? Our performance initially improved like this, and after certain time it was almost saturated with the number of layers. Why it had happened? What should be the intuition? Intuition is simple. The number of layers should be decided on the basis of the complexity of the data. What is the meaning of complexity of data? If your data is very texture rich, and the task is task is quite complex, then it is fine. But in case of signature, what is there? Only there are certain zigzag lines, nothing more than that. The background is also very simple, isn't it? So in this case, what happens after certain number of layers, your model saturates. Means enough number of features are not there to be captured. It means feature hierarchy is completed in only few layers, maybe 1, 2 layer, 3 layer, 4 layers. It is not required to use 52 layers, 102 layers, or whatever it is. It means if your data is very rich, very complex, then only you use large number of layers. Otherwise, a small number of layers should be sufficient to produce the same level of outcome. Okay, so that's why we have proposed this shallow CNN, shallow convolutional neural network architecture for signature verification. Getting the point? So there must be intuition. How many layers? Whether the data is complex, having feature rich, is feature rich or texture rich or not. If it is not, don't use much layers because it will add only complexity. Okay, and you're not going to get any benefit out of it. Okay, so this is totally intuition. This must be intuition driven. Okay. So in case of learning, so improving performance through experience and getting a computer to do well on a task without manually building competence. Yes.
Sir, excuse me. So how many layers required? Maximum how many layers we use?
Yeah, there is no absolute formula to have the number of layers. Remember?
Yes.
Okay. So now there is intuition. Intuition is simple. Means don't use large number of layers for the data which is very simple in nature. That's it.
But
So,
if output is but if output is not getting, then what I will do?
No. You will get, certainly you will get output, but the level of accuracy will not get. So normally how we use to optimize? In case suppose we need to fine tune the number of layers, then we start from less number of layers and we try to find out, we train the network and we try to find out the accuracy. Okay, and then we increase the number of layers, again find out the accuracy. If it is increasing, increase the number of layers. And after a certain level, obviously your accuracy will saturate. And sometimes, okay.
Yes.
So after sometimes it may even decrease also. Okay, so that's why that particular number of layers must be selected for your application. It is not necessary that the same number of layers will use for some different application. Remember, please.
Yes.
Getting the point?
Thank you, sir.
So again, what is deep? So for being deep, hierarchical representation is compulsory. So learning using multi-layered neural networks just for hierarchical representation of the features. So what is the relationship between deep learning, ML and AI? Again, AI is this, means, okay, you might have gone through this diagram. So AI is treated like this, ML is treated like this, and DL is treated like this. And now emotionally intelligent cognitive machines, deep learning architectures will be the future. So this way, this is simply subset. Okay, this is simply the subset. So basically this part is you can say the rule-based AI. Okay, this is learning-based AI, you can say. This is deep learning-based AI, isn't it? So why is deep learning useful? So manually designed features are often over-specified. Over-specified means sometimes you need to differentiate a man with a dog. Man with a dog. So dog may also have the black color hair, and the man can also have the black color hair. And you have mentioned that what is the length, what is the width, what is the weight, and what is the hair color, isn't it? So in case of hair color, for both it will be black. For it, either it is man or dog. For both it will be the black, isn't it? So it is not required at all. Or maybe some other features which are actually not required. Suppose whether the dog is barking or not. Suppose we are specifying this way. Is this feature useful? to classify as man or as dog? No, because it is not required. In some application, it may be useful, but here it is not required. So sometimes over-specified features, sometimes incomplete features. So some features are left by the humans to set. So either over-specified or under-specified. So that's why long time to design the features, and moreover, the domain knowledge is very important in case of typical feature engineering, or you can say the typical machine learning based model. If the domain expertise is not available, then feature specification may be incomplete or over specified. Learned features are easy to adapt. Means these are the specification based feature, means feature engineering. Here there is no feature. So these are learned feature or learning based features. So easy to adapt. So you can change the data, again features can be learned. It is not required that every time there should be some expert. Expert is not at all required to generate the features, because this is not feature generation mechanism. It is very automatic and fast to learn. Deep learning provides very flexible, almost universal learnable framework for representation, representing word, visual or linguistic information. Okay, so almost in each and every multimedia data, it may be speech, it may be text, it may be images, it may be video, whatever it is. Deep learning is useful. And moreover, end-to-end framework. So you need not to bother how to define the feature, how to find out the effective feature. And it utilizes large amount of training data. It means this is totally based on large number of experiences only. Okay. So that's why deep learning is useful. And this is typical trained. So here, SVM, decision tree, naive Bayes, etc., even neural network in general were used for typical machine learning based models. Okay. But if we find the trend from 8 to 18, how people are working, then after, it has rose from around 2012. Deep learning just started when ALEXNet was proven to give the better accuracy for certain application. Then it has increased, and now this is a trend. And now if you follow the same trend, it may have like this zigzag kind of thing, neural network. But deep learning is moving like this. This is a trend. And these models are, people stopped working on these traditional models now, because huge accuracy has been thrown by typical deep learning models in each and every domain. That's why people have shifted from traditional machine learning based model to deep learning based models. So deep learning, learning representation, or simply features. Deep learning, learning representations, means representation itself is being learned in case of deep learning. Whereas in machine learning, feature engineering was essential. So traditional model of pattern recognition since the late 50s. So here, handcrafted features were extracted. Okay, feature engineering was required. So this is typical machine learning model. But in case of deep learning model, feature extraction itself is trainable. In case of machine learning, only this part was trainable. This was hand engineered. But in case of DL, both these parts are basically trainable in nature. It means feature engineering is not at all important in case of deep learning models. So basically, if we consider the speech recognition, okay, in case of speech recognition, MELF frequencies, cepstral coefficients were extracted as the features. Then mixture of Gaussian was used in unsupervised manner just to cluster, and then classifier were used on the basis of those modified features. In case of object recognition, SWIFT or HOG based type features were extracted. So these were low level features. Then K means sparse coding. So high-level features, slightly higher-level feature were generated just by some sort of, you can say, clustering and selecting the most appropriate features by pooling and then classifier. So this was typical learning-based block. Okay.
Sir, sorry for interruption. I have a question. May I ask, please?
Yes, please.
Sir, there are satellite images where we try to extract the features. Sometimes we train the classification, and sometimes when we are doing the unsupervised classifications, it extracts and makes its own classes and then gives us the number of pixels in each class.
Yes,
So first one, the unsupervised classification can be taken as an example of?
No. Unsupervised classification?
Yeah. Can it be termed as just the machine learning and the supervised classification as, supervised classification as machine learning and unsupervised classification as a deep learning?
No. It is not necessary.
Okay.
It is not necessary. If it is using the feature, I mean, I have already told you, if feature hierarchy is not used, then you cannot consider the model as a deep learning model. Okay. So this is essential part of any learning models. Okay.
All right,
so please remember, even either in case of supervised, because supervised as well as unsupervised, both models are possible in case of deep learning as well as in machine learning.
All right. Yeah. Okay. Thank you.
Okay. So this is the means whatever we have just discussed. Suppose this is the input, then low level features will be extracted, then mid level features will be formed. Okay. And then high level features, even maybe many levels. Okay. In low level L1, L2, L3, M1, M2, M3, H1, S2, S3. And the S3 will be the highest level feature, or you can say the most abstract features. So human brains used to recognize this way. And these kind of models, that's why these kind of models have been correlated with the human brains and called as deep learning. Okay. So this way it is happening. And how these will be extracted? By the model itself. What will be thrown will be decided by the model itself. So everything is just optimization or just learning. Nothing to do with the typical feature representations. Automatically it will be done. So trainable feature hierarchy can be seen in this way. Suppose image recognition, you can consider the pixel as the lowest level feature, then edges or texton or motif or part or object. So object is the highest level of feature, or you can say the most abstract feature. In case of text, character, word group, clause, sentence, story. Speech, sample, spectral band, sound, phoneme, word. So this way, the representation, if you are doing the representation in this way, then it is fine. Okay. So typically in case of the image processing application, you can visualize those features. So that's why you can say, okay, these features are hierarchical in nature in case of deep learning models. So learning representation, a challenge for machine learning, computer vision, AI, neuroscience, cognitive science, and many more. Means almost everywhere. Okay, learning representation. So how do we learn representation is important. Means of perceptual word. So how can a perceptual system build itself? By looking at the word, how much prior structure is necessary. In case of ML and AI, how do we learn feature or feature hierarchies? In case of ML AI, this is important. In case of neuroscience, how does the cortex learn perception? Cognitive science, how does the mind learn abstract concept on top of less abstract ones? So basically these things are interrelated. Okay, so if we follow this diagram, so at every level, it is trainable from one level to the next level. So deep learning addresses the problem of learning hierarchical representation with a single algorithm, you can say. Not exactly single algorithm, but a single process, you can say. So when means how these models and why these models should be treated as a deep learning model. This is typical the ventral recognition pathway in visual cortex, okay, has multiple stages like retina, LGN, V1, V2, V4, PIT, IT, because I mean this has been taken from this source itself. So here one example of mammal has been taken, means from perception to action. How data is being perceived, means how any mammal is perceiving and what kind of action should be initiated is being initiated by it. So basically the information flows this way. Information flows this way, okay? It flows like this through variety of phases, and then action is being initiated. And various part of the brain are responsible for various types of the features, basically. So that's why in brain, mammal brain, feature hierarchy is present. Okay, so that's why these are somehow related to the deep learning model. Somehow, and people are doing very state-of-the-art research and they are proving something. They are talking about the spiking neural network and many complex concepts. But somehow, feature hierarchy is available with the brains, and that too, it should be available with the deep learning models as well. Okay. So, a hierarchy of trainable feature transforms each module transform its input representation into higher level one. Okay, and high level features are more global and more invariant. This should be understood properly. Means high level features are global features and low level features are the local features. What do you mean by local features? Suppose you're having the image, this image itself, image of a car, suppose. So what will happen if you find the low level features? Then you'll find the dots, the edges, the lines. Okay. So these are some low level features. But if we combine many edges and lines, then slightly higher level features will be formed. Even more and more, then highest level features will be formed. So basically, in case of deep learning, you can say that it takes care about the low level feature, the mid level feature, and the high level feature. All sort of features are taken care by the deep learning models. Okay, so that's why sometimes it is invariant to many changes. It means it is quite effective. So high level features are more global and more invariant, whereas low level features are local in nature. Okay, so probably you can go through many models where what happens, suppose this way units have been used. Okay, it was flowing like this. This was the input, this is the suppose output O1, O2. But what happened? It has used some skip connections have been used. Getting the point? Some skip connections have been used. Means they have tried to preserve the low level feature information as well in the decision making. While decision making, not only high level but low level features were also used. Means the model will learn in this way. Okay. So skip connections and other things in complex networks have been utilized. Means low level as well as high level features. Means local as well as global features.
Sir, please again explain it once. This is not understand clearly.
This is not understood. Okay. So I told you that high level features are more global and more invariant. But what happens where those high level features will be obtained? At the last layer. Means you have taken multiple layers. The highest level feature or more abstract features will be available at the last layer. So normally the decision will be done on the basis of the most abstract features. Got it? But sometimes for taking the more effective decision, suppose you want to generate more invariant. Suppose what is invariant? Invariant with respect to size, with respect to position, with respect to rotation, okay, with respect to scale, whatever may be. If you want to make your model more invariant towards these kind of variations, then low level features may be useful. Okay, so why not to take the decision on the basis or the aggregation of the low level as well as high level features? So in many models, low level feature information is also being used at the time of taking the decision. So this is the meaning. Okay, so
Thank you, sir.
earlier layer you will get low level feature. As we are moving down the network, our level of abstraction increases, or high level features will be obtained at the last layer. Okay, so low level features are shared among the categories. For the similar categories, low level features may be same. So that's why feature hierarchy is actually essential part. So I have discussed about these things and tried to develop one concept that feature hierarchy is very much important in case of deep learning models. So we can see state of the art in vision, basically ImageNet. So why people should use the deep learning actually? So basically some formal models came into 2012 itself for various vision applications. Okay, because deep learning models were developed for computer vision tasks, means drawing certain inferences, and later on these models are being extended in the field of image processing, like noise removal or image generation or whatever it is, for some typical image processing application. So for ImageNet in 2012, AICTE came into the picture, and this was the error percentage. So 16.4% error was reported. And in 2013, Ziller and Fergus net came into the picture, and the error rate decreased from 16 to 11. So there was a jump of around 4-5%. And then again, in 14, VZZ net came into the picture, error rate decreased to 7.3. At the same time, Google net was also introduced. So although the Google net was better, but the level of accuracy were almost similar. So both were having its significance. So Google net and VGG net in 14. In 15, ResNet came into the picture, that is a residual network. And the error rate decreased to 3.57, then 3.06, and then 2.25. So from here itself, from 15 itself, 2015 itself, these machines have beaten the humans. Means machines started giving performance, producing the performance better than the humans from 2015 onwards for typical image recognition task. So in this image net data set, large number of images were there, and machines were required to produce the class or just to output the class for any particular image. Means it has to learn, and then some unknown image will be presented to the machine. Machine need to take a decision. So since there were large number of images, huge lakhs of the images were there, then humans started failing. Humans were giving some sort of error compared to the machines. So machines were more useful compared to human for these kind of applications. So that doesn't mean that machines are better than humans, but for this particular application, means large number of images were presented to humans, and humans started failing. That's it. If you give enough time, because human learning is quite slow, if you give enough time, then humans can enhance its performance. So vision, these applications for detection and segmentation. So here now machines are able to detect persons or these kind of objects. Variety of objects in a scene can be detected. Not only that, now people have gone up to the level that depending upon those objects and their distributions, means relative placement of those objects in a scene, machines are describing what is happening in the scene. So scene description kind of activities are also possible. Okay. So people are moving. So mass car CNN. Okay. And even in case of object detection, RCNN, fast RCNN, faster RCNN, mass RCNN, YOLO, and many other SSD, many sophisticated deep learning based algorithms have been evolved. Okay, and now being used for variety of complex applications. Image generation. So these are the typical images. Okay, so what happened for this particular progressive growing of GAN for improved quality, stability, and variations. And this paper was presented in Tier 1 conference ICLR in 2018. So what happened here? Here, the data set was having certain celebrities and model learned from this data set. And what happened? After certain time, I mean, since this is a GAN-based model, generative adversarial network-based model, so this model synthesized some artificial images. Means synthesized means has generated some images which were actually not the part of the data set. But model learned that which kind of images may be available in the data set. So similar kind of images were generated, and actually these were not available in the data set. So what you can say, these are actually just like real images. It means although there is no person which is available, such person, but still these kind of images has been generated. So one way it is opening another dimension for the threat, that is adversarial learning. And adversarial learning is the big threat for the future. So many work has been done for this GAN, and people have continuously trying to improve the performance just by synthesizing the artificial images. Means actually these are not the images in the data set, but still these kind of images can be generated by using the GANs. So here you can say there are certain issues, here there are certain issues, okay, here there are certain issues, here there are certain issues which were generated by these kind of GAN, but still people are in position to produce the top class images. For vision application, Facebook accessibility tool for visually impaired people. This is another application of deep learning, image processing, and many things. And you might have sensed another tool, Google Lens. Okay, Google Lens. In case of Google Lens, you take the image of any unknown object. Okay, and it searches from the Google itself, and it throws the match that at which source these kind of images are available. So this is what? This is basically content-based image search engine. Google Lens works on that. But in the backend, deep learning-based models are working for you. Many applications. So AI beats human pathologists at detecting cancer. So this is another kind of application for variety of cancers, for histopathology and many other mammography, histopathology, thermal imaging, and other things. Machines, I mean, these AI-based, or typically you can say the deep learning-based models are being used. And everywhere those images will be used for the analysis. Vision working too well in case of the facial recognition. So there are certain controversies as well. Like if you go through these articles, then you can sense how China uses high-tech surveillance to subdue minorities. Although as per the ethics, technological ethics, it is not permissible, but China is using. So they are having the cameras, those cameras are capturing the persons passing through those cameras. Okay, and detecting the faces, and immediately observers are getting the information about those persons who are passing through the camera. Means immediately entire information can be accessed, and sometimes it is totally unethical. Suppose a person was convicted for some wrong, allegations, suppose, and he was convicted, then what happens? That information can also be used for taking a decision in future. Although the person was not involved, wrongfully he was convicted, but that decision, that information can be used. In this example, what happened? The person, just by using the facial recognition, it was assessed, okay, the person is guilty, but at the end, he was punished also. But at the end, people came to know that the person was not guilty. So these are some challenges, actually, some unethical practices, ethical practices, some threats, some challenges of these kind of models. So I was talking about the adversarial learning. So here there is example. So what happens in the original movie, the face was of somebody else. But in the fake movie, the face was of somebody else, some other person. It means by using this deep fake techniques, using generative adversarial network and other state-of-the-art networks, people are generating the face or the person or the appearance of some other person. Okay. So basically these are threats, and it is opening another dimension. So deep fakes, you can say, you can spoof the identity of some person, okay, with the help of these state-of-the-art models. Here you can observe that input is just, okay, these are the inputs. These expressions of a man are the input. These were captured, basically. These were captured. And these are the outputs. This female was there, but these expressions were transformed, okay. And now actions similar to this man were generated for this female. Okay, so she never did these kind of, she never shown these kind of expression, but these kind of expressions can be generated artificially by using the deep learning models. So somehow it is dangerous. Means you have never given any expression, but it can be generated. Okay. In case of natural language processing also, deep learning is playing very important role. And now you cannot segregate the image processing application and language processing application differently, because both humans are using both the senses. Similarly, machines are also using, means vision and language. People started talking about the vision and language, like scene description, the emotion description, and many other things. So these are the developments. So even in case of speech and language, what is this development? Earlier, people were doing some sort of research and the error rate was decreasing. But after 2000, error rate was almost saturated. Error rate was almost saturated, isn't it? People were not able to decrease the error for speech and language processing application. But with the advent of deep learning models, again, there is a sharp decrease in the error rate. And if the same is following, so we can say we are living in the era of 0.1, 0.2% error for speech and language processing applications, for those kind of tasks. But nowadays, what is happening? Even we are increasing the complexity of the task. Okay, so newer and newer applications are coming with the advent of deep learning. But yes, deep learning is very effective in almost all the domains. So several big improvements in recent years in NLP, like machine translation, sentiment analysis, dialogue agents, question answering, text classification, and many more. Okay. In case of games also, deep learning is doing wonders. Like in 1952, 1959, Arthur Samuel programmed a digital computer to learn to play checkers. Long back, it was simply programmed. Okay. In 1960, Donald Michie built a machine out of 304 matchboxes that could learn to play tic-tac-toe. Okay. This was simply, again, programming, and some rule-based systems were designed way back. But if we talk about the present day's game, so in 2013, what happened? DeepMind uses deep reinforcement learning to beat humans at some Atari games. So basically, reinforcement learning came into the picture. So reward and challenge, challenge, reward and punishment policies were used in case of reinforcement learning, and those games have been designed. Okay, Atari games. And 16, DeepMind AlphaGo system beats Go Grandmaster Lee Sedol. So earlier he was a Grandmaster, but in 2016, machines have beaten Lee Sedol and his career was completely abolished. Okay, so deep learning based machines are completely replacing the humans. In 17, AlphaZero learns to play Go and chess from scratch. These were trained, but here machines are learning now from the scratch. They themselves are learning how to play the games. In 19, DeepMind's StarCraft 2 AI is better than 99.8% of all human players. It means machines are now not only being trained, but these machines are able to learn from the scratch itself. From scratch, these machines can learn, and machines are showing the performance even better than humans. Then a day can come when machines can, machines can master the humans in almost all the domains. So this is a threat again. So these are typical examples where these deep learning models can be used in robotics and other things. So these are very early stage where image processing image processing based models were used just to actuate these artificial hands or grabber. But now these are some state-of-the-art machines. Okay, and you can see that modern deep learning based methods are being utilized for various robotic applications. Okay, and there is a spelling mistake. So embedded platforms, various embedded platforms are available for various robotic applications. Self-driving cars, so basically scenes are captured, means images are captured, and by using deep learning models, various inferences are being drawn from these scenes. Even in case of driving assistance, I can say that driver drowsiness detection is one application where images will be used, images will be captured, and images will be analyzed whether there is any drowsiness with the driver or not. There may be some thermal imaging where thermal images can be used to detect the objects in the night. Suppose you're driving the car and some object is appearing, but with naked eyes you cannot see because it is completely dark. But your thermal images, thermal cameras can see. So those thermal cameras can be used. Here at IIIT Allahabad, we have undertaken one project from DRDO where this project was on night vision. So night scenes were captured and the object was to generate the daylight scene for that particular night scene. Okay, it means if soldiers are moving, whether it is possible to perceive the scenes similar to as the scenes were in the daylight. Okay, by using some techniques. So these kind of applications are possible. So basically earlier here I'm just throwing some deep learning based models, how we have grown. So earlier machine learning basic linear classifiers were used, then multi-layer neural networks using back propagations were used. Then CNNs came into the picture. These are for typical vision and image processing application. Then networks for detection has been developed. So basically RCNN, faster RCNN, YOLO, and SSD kind of algorithms means in a scene how many objects are present. In image, how many objects are. So this is some sort of scene interpretation or understanding. Then network for dense prediction means, say we need to do the segmentation. Okay, suppose we need to do the segmentation, how to segment, or any image transformation or image compression. So these kind of networks can be used. So these are typical, you can say, unit kind of architecture or encoder decoder architecture. Then generative models, variational autoencoders and generative adversarial network kind of architectures have been used to synthesize the images, means to generate the images. Recurrent models are used where the spatial or temporal information is necessary. Suppose you need to do some spatio-temporal analysis, okay, then these kind of models can be used. Now people are using this state-of-the-art model, that is transformers. So a lot of people started doing research in this domain because the transformer performance is much better than the earlier deep learning models. Deep learning was better than the machine learning in big way, and transformers are better than the deep learning models in big way. So now people are concentrating to do the research by using those transformers. But what are the problems? Transformers are very complex in nature and huge compute power is required if you are going to use the transformers. And this is another dimension of deep learning, that is deep reinforcement learning. Okay, so this dimension is basically used in case of game and other things, gaming industry and other areas also. So how much time do I have? 5-7 minutes. So I'm just moving the slides. So convolution neural networks. So probably yesterday you were having one lecture on deep learning models. So he might have discussed about CNNs. So in CNNs, the concept of local connectivity has been used, weight sharing has been used. Why? Just to have lesser number of weights, so that if the weights are lesser, then the optimization is easy. Handling multiple input channels and handling multiple output maps. So multiple output maps will be generated. So here, suppose we talk about this layer. So multiple input channels, multiple output feature maps will be generated. So this kind of things are there. So typical models: AlexNet, VGG, GoogleNet, ResNet, DenseNet, RCNN, Fast RCNN, Faster RCNN, YOLO, SSD, and many more. CNN-based architectures are available for a variety of applications. Now, what are those applications? Image classification, then object recognition, face recognition, biometric recognition, biomedical image recognition, and many more. Object detection, so object localization, face detection, pedestrian detection, human detection, and many more. It means almost all sort of image processing and computer vision type of applications are possible with the CNNs. Autoencoder network, I have already told that an autoencoder learns the feature representation such that this latent space from unlabeled data. So basically in unsupervised manner. It contains two networks. One is the encoder. So this part will be treated as the encoder part, and this part is treated as the decoder. So encoder, decoder will learn together. Okay. And after certain time, you just simply disassociate this thing. So what happens? Some new input data, which is unknown input data, will be fed to the trained encoder. Latent space representation will be generated. So if you use this latent space directly, so you can say, okay, this is a compressed latent space representation of the original image data. And if you want to generate, then decoder latent space representation will be fed to the decoder, and decoder will generate. Suppose this is an image, and here you need to identify the crack area. Okay, so you have trained the encoder decoder for any unknown image where the crack was like this in this part only, this part of the image. Okay, you feed, then here you will simply find that the crack is in this part. Okay, so typical unit architecture is also available with this encoder. So fully convolutional networks, deconNets, SegNet, UNet, mask RCNN are the example of this kind of networks. And what are the applications? Semantic segmentation. Suppose we need to segregate the objects here. So here you can segregate, semantic segmentation, medical image segmentation, dense prediction, depth map prediction, image retrieval, image to image translation is also possible, image enhancement. What is the image to image translation application nowadays? Suppose I give simply this sketch, then can it generate the object from the sketch? Yes, it is possible. You simply draw the sketch, a machine can generate the actual like object from the sketch. So that is typical example of image to image translation. Image enhancement, noise removal, and many more are possible with the help of autoencoder decoder networks. Then we know about the generative adversarial networks. So here adversary is being used. So there are two types of network. One is the generator network, one is the discriminator network. Generator network tries to generate real like images. Okay, and discriminator network tries to differentiate the real and the real like images, are real or fake images. And this way both are being trained just by using the adversary. And after complete training, okay, these networks can be used to generate the images which are exactly same to the real images, because at that time the discriminator will fail. So this way the training will happen. These are typical GAN applications like sample generation. Here, this is image to image translation. You have given this kind of image, okay, and generator has generated this kind of image. So after complete training, almost you can say, okay, textured image can be generated. Okay. Sample generation, image to image translation, text to image translation, face post frontalization, face aging generation. Face aging generation, this is very, good application. Suppose you want to design a face recognition system which should be redundant, which should be quite robust towards the aging effect. Because aging is a big factor in case of facial recognition technology. So aging effect can be synthesized with the help of GANs. Getting it? So face aging generation, image deraining, dehaging, okay, image in painting, image super resolution. All these are the applications of image processing, because input is image, output is image. So that's why these are typical application of image processing, where GANs will be very, very useful, even in case of image compression. So one of my PhD students completed PhD in the area of image compression as well. Then recurrent neural networks. So mostly these were used in case of language processing, but nowadays CNN based, visual RNNs are being used. Okay, so where rather than taking the vectors, means one hot vector, image features are being considered. Okay, so basically these kind of transformers are inspired by, okay, CNN features applied to RNN. Okay, so recurrent neural networks. So there are certain hidden states. So here, one to many, many to one, many to many. Okay, these kind of predictions are, but this is sequence. Okay, and this is simple translation from one means many to many. Suppose this is English language. You have written something in English, and this is simply translated into Hindi. You have given one sentence, one complete sentence will be translated into Hindi. So this is typical machine translation. This is sequence to sequence generation. Sequence to sequence generation. Many to one and one to many predictions. So for these kind of applications, RNNs, so typical architectures are LSTM or GRUs can be used. So for sentiment classification, text generation, image captioning, and machine translation, these can be used. RNNs can be used. So basically, these are all applications of deep learning, okay, in variety of image and vision applications. So I'm just closing the discussion just now. If you have any queries, then we can discuss. So if you have any queries, then yes, there is.
Excuse me, sir. Are you listening to me?
Yeah, please.
Hello.
Yes, I can listen. I can hear.
Sir, is I am audible? Hello,
Yes,
sir?
yes.
Okay, sir. I have a question. I am working on motion detection using background subtraction. Sir,
Motion detection. Please.
Sir, yes, sir. I am working on motion detection algorithm using deep learning. So I am using background subtraction. So, in background subtraction, basically what we generate a background frame and we subtract the subsequent frame from the background and we get the object. So in deep learning case, what can be the training data sets?
Okay. So
Is there
what?
simple only? Is there only simple with only simple background frames? I will train the network, or like what we see in object tracking, we train the network with object also. Okay,
No,
but
no.
what
You,
is
you
background subtraction? Simply, we don't have to use the frame which consists any moving object or object.
no. Your problem is simple background subtraction or moving object tracking or detection.
A simple background subtraction, sir. Means
So
video
if it is
object
simple
segmentation using
background,
background subtraction.
yes. So if it is simple background subtraction, what can be done? Suppose your objects must be fixed.
Yes, sir.
Your objects are fixed.
No, sir. Maybe in some frame only one object is there. In some
No, that
frame
is
only
fine. One, two,
two
three is
object is
fine.
there. Some frame.
1, 2, 3 is fine, but you cannot have the infinite means. Suppose there is a scene, you must decide which is the background, which is the foreground.
Yes.
So it means
So
your
we have to
objects
train.
are fixed.
It means I have to train with both foreground and background.
Yes. So what happens? You capture the ground truth where the background should be complete white. Suppose you have you're keeping some background. I'm getting the reflection from you.
Okay, sir. So suppose I have 10 or 20 videos. So for each video, I have to train the network.
You're talking about videos. Now, just make your process simple first. Okay.
Okay.
Suppose you're having a cup. Okay.
Yes.
Then keep this cup in front of a white background.
Okay, sir.
You take the picture
Okay.
and take in all poses, all sizes.
Okay.
Means from far, from near, and all possible ways you take the picture. From top, from the bottom, from left, from right. Okay.
Okay.
And then keep this picture, this cup in front of the background itself.
No, sir. Actually, my work is on CCTV camera, where CCTV is fixed. So background will be a fixed background. Okay. So actually, I'm not getting, because object will be changing now. Maybe in some times it will be a vehicle or a man.
Actually, if your your background is completely fixed, na. So normally background subtraction means we simply subtract one frame by other frame.
Yes.
So people used to do this way so that they detect which particular part of the scene is moving. Okay. And then they simply use that part. Okay. And then they apply the object other sophisticated method to detect the objects.
Okay. So for different type of video, again we have to I have to do same kind of process.
Different type of videos means
Sir, suppose we use for our research, we use different data set, so that contain that frame captured by different type of different places of CCTV camera. Na? So for different type of videos, means different set of data, I have to use, I have to again retrain the network with the data set. I think so.
No, not like that. Because once the background is decided for any video.
Yes.
Okay. So normally background will be decided on the basis of first few frames. That's it.
Yes.
Okay. And then background will change.
But it may change. The background may change now because of sudden illumination.
That may change depending upon your deployment of the camera. That is true. But the algorithm will understand in this case.
Okay.
Yes.
Okay, sir. One my question is that I am doing image denoising problem. So what when I am patchifying the images into small patches, because we see in MNIST data set or traffic classification data sets. So this data set, for example, they have very small size, 30 by 30 or 28 by 28, because they have very less features. So it can be extracted through simple CNN and architecture. But when we are working on high level features like denoising, so we want that every edges and smooth regions should be preserved properly. So if we patchify these images into 30 by 30 or 50 by 50 and we apply the deep learning network, so what happens here, blurring extent means the output image is what some kind of blurring, okay. And even we are using 256 by 256, again these things are coming. But if we use the images of large size like 512 by 512, then it's giving somewhat good result. So what, sir, because you know that our system is not so efficient, even 16 GB RAM that we could process 512 by 512 images and thousand of images. And if we patchify, then the problems comes that blurring. Okay. So what can be the solution for that, sir? How, suppose normally we denoise or we use some images that is 256 by 256, but even it is producing a large extent of blur, sir. So is there any post processing or is there any method that, because data augmentation is also not working there properly?
No, these are basically these. Dr. Shatrugn, actually, I am getting some reflection from your
Yes, sir.
mobile audio. So actually, it is disturbing. So you can have some sort of Dr. Shatrugn, you just simply switch off your mic.
Yes, sir.
So what can be done as post-processing method? You can use some sort of super resolution. Okay, means people are using super resolution techniques to generate the images which are having better features. Okay, but your constraint, you're telling that you need to take 30 by 30 image because of your hardware constraints. Majorly because of your hardware constraints, you're not able to train with large number of bigger images. Okay, so I need to think about this problem, because if you are not, how this super resolution is going to help you. Okay, so this is another issue, because if you are processing in patches, then ultimately you need to combine all those patches and do the post processing. At the time of post processing, again you cannot process in one go. Then this is a real problem actually that needs to be thought. I am not able to think right now.
Okay, sir. One of my question is, sir, will this wider network will help to preserve the features in the output images? If we use the wider network, means parallel network, and we fuse that.
No, parallel network for what?
Sir, in denoising I have used, somewhat I am getting success, but still that problem is what you are telling, that hardware constraint is.
No. But in case of wider network, what will happen now? Again, you need to use large number of connections.
Yes, yes.
If the connections are very large, then how to optimize?
Yes, yes.
Okay, so this will be again a problem.
And then, sir, after some epochs, varying the learning rate will improve the performance. Is there any idea?
Yes, now people are using, basically, now
Yes.
people are using variable learning rate. Okay, initially the learning rate is quite high, I mean, in general quite high, and as the model is converging, if the model is converging, then they are changing the learning rate.
Okay, sir. Thank you, sir. Thank you so much.
Thank you.
Sir, you please send your email ID and contact number.
Where?
In our WhatsApp or now?
Yes, yes, just a minute. In chat box, you can see.
Yes, sir.
This is my email ID.
Thank you very much, sir. You have really explained very nicely the concepts. Though it seems to be basic concept, but you have really explained it very nicely and understandable.
So, any more questions? Actually, I have tried to develop some very essential things. I mean, sometimes what happens now, we use that, we think that this deep learning is just like a black box. Actually, deep learning is not. I mean, deep learning architectures are not just like black box. Means everything is taken just because of certain reasons. So I have not gone to those basic concepts of CNN, but yes, we should know means what kind of architectures are available nowadays, what kind of applications are, I mean, where people are involved in developing those applications. Okay, what are basic challenges and what are the threats? So these things are there. Okay, so I think that there is no question now.
Sir, you give lot of things, so very important things. So the vast area is there. So many questions, but in this small time, it is not possible to ask.
Yes, I can understand.
So very important informations are there.
No, you
Thank
can
you, sir.
ask by email, then I will try to answer.
Thank you, sir. Thank you, sir.
Yeah, thank you so much, sir, for a wonderful session and your patience. I request all the participants to join at 11:30 from the same link. Thank you once again, sir.
Excuse me, madam.
Yeah.
Ma'am, the sessions are really too good. But one request on behalf of all the participants
Yes,
is
sir.
you do have a recording of all the sessions.
Yes,
So
sir, we are having that facility.
Yeah, will you please share the recordings? Sometimes because of some avoidable reasons, some portion if we miss, so we can recap that portion just by viewing that videos also. So that
Yes,
will
sir,
be quite
of course.
possible.
Yeah,
But
of course.
usually
Sir.
I have attended so many ATAL training workshop. We go on doing the requests, but unfortunately, never we could get the recordings. And
Yes,
I'm
sir.
quite familiar with this Google Meet platform where the things are very simple, where Meet recording is one folder. If you share that folder to all the participant email IDs, so the instant the session is over, it will take some time to have that recording stored, but immediately that access will be made available to the participants. So on the behalf of all the participants, this is a sincere request for you that if you could do that, so that will help us a lot. The sessions are very
Yes, sir.
informative and will be we are finding it very useful also.
Okay, sir. We'll do that, sir. After I'll ask to my colleagues also, my seniors also. I'll tell them, and we'll be posting it in the group itself, sir.
Yeah.
Or madam,
yes.
it can be done with the YouTube channel. If you having YouTube channel,
Yes,
then
sir. We'll upload it in the YouTube channel also.
And then you can share the YouTube channel link to us. That's it.
Yeah,
Okay, sir.
that can be done. That can be done.
Okay, sir. Okay, sir. We'll do that, sir.
We also did last week FDP and created a YouTube channel and shared the YouTube links to all.
Yes, sir. Yes, sir. Thank you. Thank you, sir. Thank you so much.
Yeah. Thank you, ma'am.